Professor Pfau about interacting pop patterns.
Okay, yeah. Can you hear me? Yeah, so welcome back. And yeah, I will actually talk about a different story than what I was talking about yesterday. And tomorrow I will talk about yet another story. So these are really three completely different subjects. Today's talk is about vapor cells, that is connected to what Jim was telling you yesterday, and the integration of vapor cells with photonic networks, photonic structures. So what is a photonic structure? Well, you see one here, yes? It's an integrated optics setup. If you have ever seen an optics lab or you're working on, and you know there are mirrors, beam splitters, all kinds of elements, interferometers, and so on. And of course, modern photonic engineering can integrate all of that on the chip. So why not integrate a vapor cell on that chip as well? Why would you want to do that? Because all of what you see here, you know, is you know, here's a beam splitter, here's a ring resonator, here's a complicated interferometer, here are detectors, here are sources. All of that, what you see here, normally is just linear optics. And wouldn't it be nice to have a nonlinear element, a nonlinear medium inside these circuits? And once more, wouldn't it be nice to have one that is so nonlinear that a single photon in one of the arms of these interferometers, for example, makes all the difference, meaning that one photon can cause a phase shift on another photon by pi. If you can do that, that's the holy grail. Yeah? If you can do that, then you can build a phase gate, a controlled phase gate. The photonic platform on quantum computing right now doesn't have that. It is all done by the, post selection on events, on the detection side, or by, producing interesting entrance states in those linear optics interferometer setups. That is doing all the work in quantum information processing and so on at this point. Yeah. And that is because nature does not usually provide materials that make two photons interact strong enough. Okay, so of course, you know, here in the room, the two photons will just penetrate each other and not interact at all. Yeah? But if you have a medium, then you can construct a nonlinear behavior. And it turns out atomic vapors, atomic gases, are pretty good media in terms of nonlinear optics. I mean, they are not straightforward to make it a nonlinear medium at single photon level, but that's where we are heading, basically. And I'm telling you how far one can go there. Okay, this is the group of people working on this in my lab, my institute, and we have a strong collaboration both with Purdue University, that is Hadize Alayam. She was a group leader in this project for 3 years in Stuttgart, and now she is an assistant professor at Purdue. And Charles Adams at Durham. So we have members from Purdue here and also from Durham here, who actually joins us on a weekly basis in our online group meetings. Now that is actually one of the good things about the pandemic. Very famous people like Charles, can become a team member by just joining our group meetings. Yes, so we are very thankful that this is possible. Okay, yeah, it's also a giant project, by the way. Okay, so here you see a typical integrated photonic setup. It's actually a simple one, yes, where you see guiding structures that curve around, you see that two guiding structures can touch each other. That means that the photons can tunnel, if you like, from one guide to the other guide. And you can see that we are using so-called Bragg couplers here, which means that we are shining the light from the top, and then there is a grating that is diffracting the light into the guiding structure. So the light comes from the top into one of these couplers, moves around, and then exits here again. And so if you look at this chip from the top with a microscope objective, you see the light coming back out at one of these couplers at you. So what can you do with this? Yes, I mean, first of all, it's small. Yeah, so it's like, this is a 50 micrometer scale. Yeah, so all of this is this optical setup is much smaller than any setup we have in your lab. Yeah, it is perfectly aligned. Yeah, if you have ever worked on an optic setup, that's something to highly appreciate at some point. Yes, it's very robust. Yes, it is scalable. Yeah, you will see that the structures that we are using come not only with one such setup, but with hundreds of such setups on one chip. Yeah, so we can vary the setup and manipulate it. Then it is possible to tailor the light fields that you are working with, and I will show you an example. For example, you can take a beam of atoms that if it's freely propagating, you know, you have a hard time to focus it down to 1 micrometer. Yeah? But in the integrated photonics, it's actually easy to have a mode that is that well confined. And what's more, if you design the dielectric environment of that waveguide, you can confine the light even to a size that is much smaller than the optical wavelength. I will show you a mode that we are using where the light is traveling in a mode that is only 50 nanometers wide. So if you are squeezing all your photons through such a small mode, obviously the field per photon is already enhanced. That's very good for nonlinear optics, of course. Okay, so that's what I mean by tailored atom light interaction. Yes, you can tailor your light field, and you can also tailor the spot where the atoms are going to interact. How do we do that? Well, let's look at this thing down here first. Or maybe I should show you the full thing. The technology that we are using is either based on silicon nitride, that is a light guiding medium, or on silicon itself at 1.5 micrometers. And we are using these Bragg couplers here. And we are using also a glass silicon dioxide cover on these structures such that the guided light is protected to the outside world everywhere except at one interesting position, namely, for example, in that interferometer here. Yes, so the light is guiding without seeing, you know, the external environment, just this glass, you know, that is not interesting. But at this position here, atoms will be able to interact with the evanescent field, for example, of these guided photons. Okay, so you can tailor the position where the atoms are, although they are everywhere in your vapor cell, but on the chip, you can say, okay, I want them to be here. Yes. And the experiment is actually fairly simple. You just have that structure here. You make a cell, put it in an oven because you want to vary the atomic density by just heating the cell up. Yes. And then you observe it through a confocal microscope, either with a camera or with a photomultiplier. Okay, so you couple in on one side, let's say here, go through your structure and couple out on the other side. So this is how such a cell looks like. I mean, this is one of these chips that we get from various partners that are making them for us. You see a little bit of rubidium here. This is metallic rubidium. It looks like silver. And that is connected to that volume here. Now the structures are upside down, so they are in the inner part of the cell, obviously. Yes, but you can still couple in from outside and through these Bragg couplers into these waveguides and couple out again. Yes. Okay, and on the inside of that chip, you now have the chance to have lots of optical setups at once. Yes, you see every little square here, you know, is one structure, and you can, once you have the chance to design such a chip, you can design experiments for 5 PhD theses and make one cell, and then everybody is busy investigating this cell. Okay. Good. So what can you do? Yeah. For example, just you know, these are now linear optics examples. Here you see an input coupler. The light is propagating this way, and it comes out on this side. Yes. If you do it with 780 nanometer and you fill the cell with a medium, yeah, then you have a resonant medium inside, and you get the normal absorption. In this case, we were not satisfied with this. We wanted to do a counter-propagating experiment to get the Doppler-free signal. And we used this input port to let another laser beam counter-propagate here at 776. Some of you know that the video has this transition from the upper P state to a D state at 776. So you get a counter-propagating spectroscopy, and all of a sudden you get a line width that is no longer Doppler broadened, but is more narrow here. Yes, and you actually already see the line shape is a little bit asymmetric. It's interesting. There are surface effects, but there are of course also transient limitations because the atoms interact now in this open region here as they fly through the evanescent field of that guided mode. And that evanescent field is of course only, let's say, a few hundred nanometers thick. And if you calculate the transient time of atoms flying with a few hundred meters per second through that thing, you end up with this transient broadening that you see here in that spectroscopic signal. You can do many more things. Yeah, you can do this interferometry. Yeah, you see one arm is a reference arm that is covered with this glass, such atoms do not interact. And then here we have an arm that is interacting with the vapor, and that can be detected then as a function of the tuning as a phase shift. As you go over all the resonances in rubidium, you see a dispersive signal at any time you hit a resonance. Yes. So you can do interferometry and measure the phase shift due to the medium that you're putting there. Okay. You can make ring resonators here. A ring resonator is an optical resonator that has a resonance line width. It's actually this broad feature here. And on top of that broad resonance of the optical resonator, you can now look at the more narrow resonance of your atomic medium, and you see that these atomic features here can be shifted around if you tune the resonance frequency of your resonator, for example, by the temperature. So these are just examples of, let's say, absorption or dispersion, just linear optics effects of these media of this atomic media in a photonic circuit. What is also interesting is that the rubidium atom provides you with a wavelength from that excited P state that is 1.5 micrometers. That's interesting because that is a wavelength that is transparent in silicon. So silicon photonics can be used in connection with vapor cells as well. And I will show you some more examples of this. Yes. So a cell with silicon photonics looks like this. By eye, it looks black, yes. But of course, at 1.5 micrometers, it's highly transparent. It has very good optical qualities. Okay. Now, we wanted to talk about nonlinear stuff, not just the absorption and dispersion. Yes. So for nonlinear stuff, we need interactions. Yes, and that's where Rydberg atoms come in. Yes. And you have heard of the Rydberg blockade, but I realized so far nobody really talked about it in the talk, so I just flash it here for you again. Yes. So what's the idea? You have two atoms sitting at the distance r, initially in the ground state down here. Yes. Then you take one or two photons to excite one of them to the Rydberg state. Yeah, let's call this Rydberg state the excited P state here. Yes. If one of them is excited, not much is happening, I would say, on the scale we are interested in. Something is happening, there are alpha long range molecules and so on, but these are weak interactions. So I draw a flat potential, although we know it's not really flat, but for this purpose here it's flat. Only if I excite the second one also to the Rydberg state, then I get very strong interactions. And there's an interaction potential. For example, in this case, a repulsive van der Waals potential that scales with 1 over the distance to the 6th power. Yes. Now, if I do this excitation with a line width gamma or a power broadened laser that is broadened by Rabi frequency omega, then this interaction leads to a blockade effect, meaning that if these atoms are sitting closer than the blockade radius, that is just given by equating this van der Waals potential here with the line width of your excitation. So if your two atoms are sitting at a distance shorter than this blockade radius, you cannot excite it. It's blocked here, yes, because your laser will not be resonant with this interacting two-body state. Okay, so if you have a medium like this, lots of atoms, you send your laser beam through. The Rydberg atoms have to keep a distance because of that blockade effect. And the length scale that is introduced here is this blockade effect. Yes. So every Rydberg atom makes sure that around it, basically, there's no other. So if and these blockade radii basically are on the order of micrometers. If you do the experiments with cold atoms, then they can be tens of micrometers even. If you do that with vapor cells, with hot atoms, they are still on the scale of a single micrometer, for example. So larger, much larger than the optical wavelengths, for example. So let's think about this situation where we single out by just making a very small glass volume, yes, where we have thermal atoms inside. And let us just single out one vapor cell that is smaller than this blockade radius. Okay. So what's happening? We call this a superatom. This volume, although there are thousands of atoms inside, can only be excited once to the Rydberg state. But we don't know which of these 1,000 atoms actually is the excited atom. Yes? And in quantum mechanics, if we don't know, yes, and the phases are preserved, then we have to write down a collective excited state where either the first one is the excited atom and all the others are in the ground state, or the second one is the excited one and all the others are in the ground state, and so on. It's a big sum, yes, with 1,000 terms now, let's say, or the last one is the excited state. Now, you have to build the norm here. So you have to have a 1 over square root of n, where n is 1,000, the number of atoms in that cell, is in front here, yes? So this superatom, this object here, made out of 1,000 atoms, has one excited state. That's this state here, yes? And one ground state, of course. Everybody is in the ground state. And if you connect them with a dipole transition, there's a Rabi frequency. But if you think about this now, you have to build the matrix element between that ground state, which is a simple product state, with this W state. Some people call this a W state. Yes, if you have a single excitation distributed over many other atoms, they call it the W state. Yes. So if you do the calculation with a single atom Rabi frequency omega 0, you see that the collective Rabi frequency is enhanced by a factor of square root of n, because there are n terms here, but you have to divide by 1 over square root of n. So what is left is square root of n times omega. This is a brilliant idea. Yes. I mean, it goes back to a paper Misharukin and others 20 years ago. Yes. It provides you with the concept of a two-level atom, although you don't have perfect control over the 1,000 atoms inside the vapor cell. it actually does not require cold atoms at all. You can do it at room temperature. That's what we are going to do. Now, of course, you have to ask, how long is this is the coherence prevailed? I mean, of course, we have plus signs here, yes, and if the atoms are moving around, this state will quickly dephase. Yes. So how fast will it dephase? Well, if the atoms move fast, then it will dephase quickly. Yes. But if you think about it, this is exactly the Doppler width of the transition. So the Doppler width is on the order of 1 gigahertz, so the typical coherence time is 1 nanosecond. So if you want to do this with cold atoms, then this coherence time is much longer, and you have microseconds time to do the experiment. If you want to do this with vapor cells, you just have a nanosecond to do the experiment. So you need pulse lasers, fast lasers. Yeah. That's the price you pay for having hot atoms. But pulse lasers, nanosecond, are available. Yes. And a nanosecond pulse is not that short, actually. It's actually quite a long pulse for a pulse laser. Okay, so if you want to use that blockade effect to build a quantum device, let's say a single photon source, yes, then what you want to do is you want to bring that single excitation in that Rydberg state back down and convert it back into the light field such that a single photon comes out. Okay. So this is actually called four-wave mixing, a nonlinear optics phenomenon. Yes? And the way we do it in the experiment is we take the atoms via a 2-photon transition to the Rydberg state on one route, let's say the T2 line in rubidium, and we take this excitation back down again on another route, let's say the T1 transition, such that this photon that is eventually coming out can be filtered against this strong drive field here. Yes? So it's non-degenerate four-wave mixing. That's the thing. Yeah? So we have the superatom plus four-wave mixing, and the result is a single photon that is going to be emitted in a forward direction, because this object is much larger than the optical wavelength. So if you think about it, all these 1,000 atoms are going to radiate in a collective way, and they know how they were excited. The phases of the excitation lasers are imprinted there. So they're gonna, if we are shining all the lasers from one side, this emitted photon will be emitted in the forward direction, not just randomly in 4 pi. It's a coherent process, actually. So this has been demonstrated for cold atoms in this pioneering paper here by Alex Kuzmich group. At the time, he was at Georgia Tech. What he did is he took a small ensemble of cold atoms in a dipole trap, and he just did exactly what I said. There's this four-wave mixing, and he measured then how good a single photon source he could make with this. Yes? And here you see the result of the G2 of 0. So, you know, if you measure the statistics of light coming out of a source, one thing you can do is measure the 2-photon correlation, G2, intensity correlation. And if you have detected one photon, you shouldn't detect a second one. Yes? That means that the G2 is 0. And he measures this G2 as a function of the principal quantum number n for his setup. And then if n is small, the interaction is not strong enough. You see that there are 2 photons coming out of this experiment. But if the blockade gets better and better for principal quantum number 80 or higher, the G2 approaches 0. So it looks like a perfect single photon source. So, and this challenged us, and we wanted to do this for thermal atoms. Okay. So how do we do it? We have to make a very small volume of thermal atoms. The way we do it is we make a vapor cell that is very thin. let's say 1 micrometer. Yes, it's a piece of art how to make this. If you want to know how to do it, you can ask me. And then you take 2 lenses here, and you focus your laser beam also to 1 micrometer inside the vapor cell. That's also not fully trivial, but possible. And then here you actually see Robert and Harald making cells, yes, with the flame here and so on. So you have to have glass blowing skills. But actually, we do have a professional glass technician also in our university. And so you make a cell that looks like this. If you look closer, you see the Newton rings, yes? Because the 2 glass plates are so close to each other that you see the interference, even the white light interference, showing the colors of the rainbow here. Yes, this is the interesting area of that cell. There, it is essentially 1 micrometer thin. Okay, then you put this. This is a picture of the setup. You put this cell between 2 lenses. These lenses have to be corrected for the thickness of the cell, such that you really get a diffraction limited spot inside the cell. But never mind, you can get a focus in here that is actually a little bit smaller than 1 micrometer. Whoops, a little bit smaller than 1 micrometer, and the thickness is 1 micrometer. So you have singled out a cubic micrometer. Yeah, that is this super atom. Yeah. Now you can ask, what kind of atom should I take to do this experiment? And there are many choices. I just show you a comparison of rubidium and cesium, and why it makes sense to think about this beforehand. Because if you do an experiment on the nanosecond time scale, nanosecond pulses, the bandwidth that you are going to have in this experiment is 1 gigahertz. Yes? So the potential curve of the Rydberg-Rydberg interaction should be clean in all the way up to several gigahertz. Yes. So what you see here is a nice example, internuclear distance or interatomic distance of the Rydberg-Rydberg interaction. In this case, for the 32s asymptote. And if you go to shorter distances, you see that the potential looks nice all the way up to 5 gigahertz. Yes. No, it's a repulsive van der Waals potential and not a lot of trouble to be expected. However, if you do the same thing with cesium over here, 32s, you follow this potential, you see, oh my God, there is a lot of crossings and avoided crossings and looks very messy. Yeah? So if you would do this experiment with cesium, with vapor cells, it would not work. It would work for cold atoms, yeah, because out there at the bandwidths in the megahertz range, it's fine, yes. It looks like a clean potential out here, but at short distance, it looks like thickness. So you better do this experiment with rubidium. Okay, so that's the scheme then. I said it the wrong way around. Yeah, we do it on the D1 line up and the D2 line downwards. Okay, and then we detect. These are the pulses that we are sending in, and the important thing to note is these are nanosecond pulses. Yes, 0, 5, 10 nanoseconds. So we are sending these 3 waves in simultaneously, and we are observing what comes out on that final transition. And we get a signal that looks like this. And you can see, okay, it's a complicated thing. Yes, it has a peak here that is relatively short, just a few nanoseconds long, and then there's a tail of decaying light. Yes. So what's going on? Well, the 4-wave mixing process is a coherent process. So it only happens as long as your driving fields are on. Yes. So if you have a nanosecond pulse, you expect a sharp peak here due to the coherent 4-wave mixing emission in the forward direction. And if something goes wrong, like you dephase the system, or there's you dephase the superatom, then you still have this excitation around, but it will just decay via spontaneous emission, for example. Yeah. And so then there's an afterglow basically at a much longer time scale, because you should remember the lifetime of that 5T state is about 30 nanoseconds. So much longer than any of these pulses. Okay, now if you focus your analysis, now you're detecting this not with just one photodetector, but with two photodetectors, so-called Henbury-Brown twist setup, yes, where you can then also measure the G2 correlation function. Ask the question, are there ever two photons coming at the same time? Then you see that in this experiment, the G2 can be suppressed way below 1. It's not perfectly 0, but it's 0.2 or something like this, if you analyze the data in the first few nanoseconds. Okay, so only in the region of the emitted light where you have this coherent emission, this forward direction, the four-wave mixing, you have a single photon source behavior. Now you can do many experiments. You can change the cell length. Make the superatom big or large compared to the blockade radius. This way you can start with a cell length of 0.6 micrometers, so 600 nanometers. There the blockade is nice. You get the suppression, but then if the cell gets up to 1 micrometer and larger, the blockade is over. Yes? And you are back to normal emission where the G2 is actually 1. Yes? If you then analyze this tail here, this afterglow, that's the red points here, you see that this is also just normal scattered light. Yes? It doesn't have this quantum character of a single photon source. Okay, yeah, you can vary this time across here. You see, yeah, only the first few nanoseconds, you get this coherent behavior that is, responsible for the single photon character of that. If you make this upper time of your analysis longer and longer, you see that the dephasing kicks in, and that way you can actually measure the dephasing time, which I predicted to be a nanosecond or so, 1 or 2 nanoseconds, and that's exactly what you see here. Why? Because that is the Doppler width of our ensemble, the inverse Doppler width. Okay, so this was a proof of concept experiment to show that you can use the Rydberg blockade. First, you can demonstrate that the Rydberg blockade is actually present at room temperature or even above, because we have to heat this cell to 160 degrees C. So it's hot, you will burn your fingers. Yeah. So it means we can create this W state, which is a highly entangled state, in this hot environment and keep it alive for 1 nanosecond. Yeah. We prove this because we are sort of transferring it back into the light field, and then the light field shows exactly this quantum behavior. Okay, but so it's a nice proof of concept. Let's say that thermal vapor can show quantum effects on the single photon. But practically, it was very difficult. Yes, the lasers are pulse lasers. The whole experiment has a repetition rate of 50 Hertz. So it's not a useful single photon source yet for any application, let's say. Yeah? But we are working on this. We have now changed our scheme to an inverted scheme. So we don't go to 5P now, we go to 6P, which means that these upper lasers are now in the range of fiber laser amplifiers at 1010 and 1020 nanometers, where we can get repetition rates of 1 megahertz, yeah, which is more interesting for quantum communication applications. Then the single photon that is coming out is at 420, the blue. That's a little bit unusual, but okay, that's how it is. Yes. So we are working on this. We have a 4-wave mixing signal in the scheme with nanosecond pulses, and what it tells you is, maybe that's interesting also for people that are working on Rydberg quantum computing, Rabi frequencies in this kind of scheme can be much larger than a gigahertz, because that's what you need here. Yes? So you just need the right laser sources, not CW sources, but pulse sources that are phase coherent, that bring you all the way up to the Rydberg atom in a nanosecond, or actually much less than a nanosecond. And usual CW lasers that you have in your lab to do the Rydberg excitation wouldn't do this for you. But these ones are doing it. Yes. And of course, now it's time to check for other properties of that single photon source. For example, we have to check for indistinguishability. Yes, the whole idea of this is that once you have such a concept of a single photon source, you can scale it up to many. Yes, because I mean you cannot only have one such spot in a vapor cell; you can have as many as you like. Yes, and the single photons that come out, hopefully, I mean that's what we would predict, are all identical. Yes? It's not like with quantum dots, yes, where you or Henry centers or so, where the environment is shifting the frequency around at every spot, and it's very hard to find two identical quantum dots that are producing the same identical photons. Yes? But with this approach, we think it should be possible. Yeah? But we have to demonstrate this, of course. That's one of the future tasks. And then, of course, this didn't have any photonic circuit yet. Yes. And we have to make an effort to integrate this. Okay. How am I doing? Okay, same time. Now, I'm not talking about the integration part. I mean, if you're interested in that, please ask me. But that's just a technical thing, how we are planning to do that. It's more about the physics. I mean, we have now seen that we can get a nonlinear behavior if we let the atoms interact strongly, yes, via the Rydberg interaction. And we were doing this experiment in a regime where the density times the blockade radius cubed was much larger than 1. That's strong correlation, strong interaction condition. Yeah? If you look now in the vapor cell, it turns out you can get densities that are so high, much higher than in any BEC, for example, such that the atoms are even closer than the optical wavelength. So that condition is n times the inverse of the k to the third power, can be much larger than 1. Yes. So these are very high densities, and we can also get strong interactions even without the Rydberg atom. Okay. Let's think about this, because that's much easier eventually to do. And that brings me to the talk by Stephen, where I see he has talked about the energy transfer, yes? Which goes back to Theodor Förster. I have the same reference, but I noticed you had a reference on 32 from someone in France or so. You should give me that reference, because I'm not aware of this. Because I have to mention Förster, of course, because he was a chemistry professor in Stuttgart, where I'm from. So proud of this. So what is this? I mean, he explained it already to me. Yes, if you have two level systems that are, say, resonant to each other, either it's helium, what was it, Rydberg, and ammonia, with a two-level transition that is tuned into resonance to each other, or you have two identical atoms, like say rubidium and rubidium. Yeah? Then the following can happen. Yes, the two eigenstates, the ground state and the excited state, in this case, let's say, are S and P states. Yes, every eigenstate doesn't have a dipole moment, yes? But if you bring them close enough, they start to interact in their near field by the dipole-dipole interaction. So if you start with a situation where one atom is excited, the other one is in the ground state, the one is S, the other one is P, this is not an eigenstate. The system will start some dynamics. It will de-excite on that side and transfer the excitation to the other side. It's actually an oscillatory process. Yes, going back and forth. And in between, you see that the superposition states between excited and ground state, of course, do have a dipole moment. So if you bring these two-level atoms close enough together, they experience a dipole-dipole interaction. And that dipole-dipole interaction leads to shifts and broadenings, as you will see.
Right, so
Yeah.
why do you say they have to be in your field?
Oh, okay. So there's also something happening in the Pfau field. There are retardation effects that you have to take into account because light propagates at finite speed. But I want to keep it simple, yes. But I fully agree. I mean, there is some effect also at longer distance. But what I want to, so this is the full formula of that dipole-dipole interaction. And what Chris is referring to is this back part here. But what I'm going to do now is I just get rid of it because I'm just looking at atoms at very short distance. So a distance smaller than the wavelength over 2 pi. Then I'm in the near field, and then the interaction is the strongest. This is this regime that I want to be in. That's this n divided by k to the power 3, much larger than 1. Yes, then at least the next neighbors are in the near field. And then it's very easy to understand the physics here, yes, because it's just dipole-dipole interaction again. With all its angular dependence. What was on the previous one? Let's just. Yes. So if you have dipoles, then you can have a situation when they are sitting side by side. Just like magnetic dipoles, here it's now AC electric dipoles, they are sitting side by side and they repel each other. Okay. So this will shift your resonance frequency of the whole system to the blue. There will be a blue shift in this ensemble. If, on the other hand, you have them sitting head to tail, like this, there will be a red shift. And now you see that everything is geometry dependent, yes? Due to the anisotropy of the dipole-dipole interaction. So if we want to estimate how large these shifts and the broadenings are, then we have to consider certain geometries. Let's start with a cube here as an example, where I'm having a probe atom, the black atom in the center. It's surrounded by blue guys in the plane and red guys head to tail. If you do this integration over the whole angle, then it turns out the interaction is 0. Yes, because there's as much repulsion as attraction. Okay. However, if you now change your geometry, for example, you make this cell thinner than the wavelength, yes? Then you see that there is a shift that is dominated by this head-to-tail configuration that is red shift. It's a red shift. Yeah. And we can investigate this, yes, in these thin cells. There's another example here, yeah, where you again see these rainbow colors. You can make very thin distances between the glass plates, and you can investigate, I come to that in a minute, this redshift. Yes. But you can also go the other way. You can make the cell very long. Then the blue guys, there are more blue guys than red guys, and this repulsive force of the dipole-dipole interaction is dominating. And you get a blue shift. Now you might ask, why do all these arrows point in the same direction? Well, that's the light polarization of your driving field that is exciting the dipole in a certain direction. Yes? So you also have to control the light polarization in your setup. Now, how can we do that in the experiment? How can we get, let's say, such a one-dimensional chain of atoms in a vapor cell? Well, the way to do it is to use something that is called a slot waveguide. It is guiding the light. There's a dielectric structure made of, in this case, silicon, a bar here, another bar here, and the light is guided along in an open gap between those two bars. This gap is only 50 nanometers wide. And that's where you're squeezing your photon through. Yes? So just show you this first. This is the structure where we do the experiment. Yes. We couple in with our brake coupler and couple out on the other side. And then in the middle, there's an open region. But this time, it's not just a single waveguide. It is a waveguide that has a little cut in the center. Yes. And if you, so here is an electron microscopy picture of that structure. This gap here is about 50 nanometers only. Yes. Much larger than the wavelengths now. Yes. So transversally, clearly, it's in the near field. Everything is in the near field. Yes. And if you think about or calculate the field distribution of the guided mode, you can choose the geometry such that all the field strength is concentrated on in the gap, inside the gap. Yes. That's ideal. Yes, you want to let the atoms in the gap interact with the light field. Yes. Normally, what I showed you before, the atoms were just interacting with the evanescent field, and that is sort of the weakest part of the whole mode. Now we have, now we have a guiding structure that funnels the photon in that gap, and even enhances the field strength per photon that is going to interact with the atoms. Okay, called the Purcell effect. Okay, and again, you can't really see it very nicely, but here there are many such structures with different widths and lengths and so on. That's that you can investigate. So the experiment goes the following way. Yeah, it's a silicon photon structure. So what is coupled in here and out is a 1.5 micrometer laser that drives this P to D transition. And in order to bring the atoms into the P state, we just shine a red laser from the top. This way we can, control the density actually on a very fast time scale if you want. Because we just switch on and off that 780 nanometer. Okay, so let's look at what happens. Yes, we look at the absorption. Yes, as a function of the probe power and the detuning. That's the other axis here. And the first thing to note is we are talking about very low powers here. Yes, femtowatts is what we are. The experiment is happening on the femtowatt level. I promise you, yes, it will be a few photons only. Yes, that make all the difference here. Yes. So here's 1 femtowatt. Here's 0.1 femtowatts. Yes. And an atomic medium is non-linear because it's saturated. So where is the saturation happening? Well, it happens about. That's my pointer. Doesn't work anymore. Oops. Go on. Okay. Low battery. Do it here. Okay, here, yeah. So it happens at around a little less than 100 femtowatts. That's the saturation behavior. You can measure this by just measuring the width of the absorption. Yes, as soon as this gets broadened, power broadened, yes, then you saturate the transition, and that's a nonlinear behavior. Yes. Okay, so now you can study this in some more detail for different densities. So this is a lower density, 1.5 in these units. Mean distance r times k to the power -3. So that's ranging from 1.5 to 6.7. And you see that you not only get a broadening of that line, but also a shift. That is what is plotted here. Yes, that's the line shift due to that interaction. And I try to explain to you that what we expect in this one-dimensional geometry is a blue shift. So that's a positive shift here. And we measure it in units of the line width, gamma. Yeah, sorry, my pointer is running low here. It's gamma 0, yes. So what you can see is that we get shifts. This is now the probe intensity in units of the saturation intensity of the transition, yeah, that are on the order of 100 line widths, yes, of the transition. So that's, it's a sizable interaction. Yes. And the blue stuff in the back is a model that we do, where we take atoms moving around and we let them interact via that dipole-dipole interaction. It's a Monte Carlo simulation. Okay, so we can measure now the line shift, the maximum line shift that you get as a function of the density. And you see there's a linear scaling. And if you compare it now with the free space theory, you see that this shift is 8 times larger than what you would get in free space. Why is that? That is the effect of that Purcell enhancement, namely that the photon is squeezed in the transverse direction into that very narrow slot. Yes? And why is that important? Well, if you go back, if you have a shift in your system that depends on the power, yes? You see the shift is there for low powers, but it vanishes if you saturate the system, yes? Then this is a nonlinear behavior, yes? The power-dependent behavior. It's a chi-3 nonlinearity. Right? And you can calculate how nonlinear that is. And of course, it becomes more and more nonlinear the larger that shift is here. And obviously, I mean, here we have a maximum density of 6.7. But if you want to increase the nonlinearity, you can just make your sample more dense. And I come to how we can do that maybe in the future. But if you calculate now how nonlinear it actually is, then you see, okay. I didn't even put it here. Yeah, then you see that a few 10 photons are enough in this experiment already to cause a phase shift of pi on another photon that is transmitted. So it's not a single photon nonlinearity yet, but we are just about 1 or 2 orders of magnitude away. And now if we increase the density by 1 or 2 orders of magnitude, then we would be there. So how can we do that? Well, this experiment was a CW experiment, yes. And there is a CW density in the vapor cell just by heating it up. Yeah. But there are other methods that you can use to increase the density locally by orders of magnitude. And that is called light, the technique that we are using here is called light-induced atomic desorption. So if you think about the vapor cell made of 2 glass plates, then there is the vapor between the 2 glass plates, but there's also a coverage on the glass walls. Rubidium atoms just get absorbed there, and they're sitting there. So these are the blue guys. Yeah. And if you now hit those atoms with a strong laser, not resonant with anything, just a green laser that provides, in this case, a nanosecond pulse to you, then you will lift these atoms off the surface, and they will, for a short time, increase the density in the cell by up to a factor of 100. Exactly the factor we need. So we investigated this. So what happens here is that the atoms start to leave this surface and they move over to the other surface. And actually the same thing happens on the other side as well. So if we look at this desorption as a function of time after this Lyot pulse, as a function of the laser detuning, then we see, okay, let's look at this graph here. Before the pulse comes, there's a certain absorption because of the vapor, but then when the pulse comes, boom, the cell becomes optically thick, and the optical thickness recovers then. Right? And this all happens here on the time scale of tens of nanoseconds. Now, if you have a probe laser that has a certain detuning here, then you are probing different velocity classes, and you see, of course, that you have a Doppler width, again, on the order of 1 gigahertz here. Yeah. And you also see that the fast guys with the large Doppler detuning hit the other side of the cell first and vanish. And the slow guys, they stay a little bit longer, yes, before they vanish into their motion to the other side. And that's actually that green envelope curve here, yes, green dashed envelope curve. So yeah, this is the setup. We shine this light pulse through the cell, and we just measure the transmission as a function of the frequency. So we can do this with low desorption power. We are talking about megawatt per square centimeter here, and we can increase the pulse energy or the intensity, the peak intensity from here to here by a factor of 100 roughly, and then get more and more atoms. And if we get more and more atoms, then also something interesting happens. Namely, the density becomes so large that we get dipole-dipole interactions. Of course, yes, this is not a waveguide experiment now, it's just a normal vapor cell experiment. But as promised, if you have a very thin ensemble, yes, then you expect a redshift. And that's actually what we can see. Yes, this is very related to what Charles Adams has done years ago. We can also do that on the two different lines, the D1 line and the D2 line. So I don't go into the detail. You can measure as a function of time after such a light pulse, the line shift, again on the order of 100 line bits here, and a broadening. And as both of them, both these transitions have a dipole moment that is actually different, yes, D1 and D2 line have a different dipole moment, the shifts and the broadenings are different. And we can build the ratio and convince ourselves that this ratio corresponds to the ratio of the dipole moments squared, actually, that you should expect here. Okay. To summarize, I have shown you in the final part of that talk, the second part, that we can get strong nonlinear behavior in integrated photonic circuits due to the presence of atomic vapors. We have already seen a per cell enhancement of a factor of 8 compared to free space, just by confining the light in these dielectric structures. And in the other part, I showed you that if we use this light-induced atomic absorption technique, we can increase the density even by a factor of 100 above what we have used in this experiment. So obviously, we have to combine the two things now and make an effort to realize a single photon source. And that would be nice, coming back to my initial picture here, because if you think about this, this nonlinearity can be controlled very well. Yes? The light pulse can be focused anywhere on your chip. So you can say, okay, I want to have my nonlinearity here, yes, for 10 nanoseconds. Yes, then I fire a laser here, and I get a nonlinear effect here. Yes? Or I do it here or there, or I do at many places, and I can basically control this nonlinearity at will in space and time. Yeah, so that's what we are aiming at. And then there are other things that we are also doing. Of course, in order to enhance that percent effect, you want to work with cavities, not just waveguides, with the resonance structures. So, for example, it's hard to see here, but these are these photonic crystal waveguides where you are sort of building a cavity around a certain position, and then the electric field enhancement per photon is even much larger. Yeah? So this is another front where we can improve the situation by just increasing this per cell effect. Okay, and with this, I want to thank the team again and you for your attention.
Talk about this single photon source. However, you don't know how many atoms are actually in this
Yes.
Blockade radius.
Yes.
So, I mean, it's still a statistical source, right? It can be one photon, or it can be two photons, maybe in a certain time, one photon.
Okay.
So it's
So,
not like I want to have something where I press a button like a photon.
yes. So there is, although I'm not sure at any moment whether I have 1,000 or 1,050 atoms in my cell, I am sure that there's only a single reflective separation. So what you are referring to is that there is a fluctuation in the collective Rabi frequency. Okay. But the collective Rabi frequency does not directly go into the photon. Yes. It is just, it's actually very, how do you say, it's not susceptible to this fluctuation. The whole system.
So you rely on this decay, right? That's the process.
Yeah, but it's a decay. It's not a decay. It's important to distinguish this. This is a coherent radiation of all the dipoles that are excited simultaneously. But overall, all the 1,000 or 1,050 carry a single excitation only.
Yeah, so, but the point is, like, they might decay in the pulse, they might decay once, they might have not decayed, they might decay twice. So it's
not twice. How can they decay twice? There's only a single.
Can they decay once and go up again?
No, how can they go up again?
Where you still have the pulse on.
Ah, okay, okay. Let's go back. Yeah, that's something about the timing of the pulses. Yes, and that's a good point. Yes, that's actually something that we are working on as well. How is the optimal? How is the optimal pulse shape? Yes, it's an optimal control problem. So ideally, what you want to do is you want to put everything into the Rydberg with the first two pulses, then switch them off, and then take the third pulse and bring it all back down. Yes, because of what you say. Otherwise, there can be a re-excitation or something. So that would be on paper, yeah, the ideal situation. Yes. However, you have a decay rate here, or dephasing rate, I should say, that is on a similar time scale in this pulse length. So then you have to make a compromise basically. Yeah. But what you see is that already for a non-optimized situation like here, we get a sizable reduction in the G2. It's not zero, yes, it's 0.2 here. And some of the infidelity, let's say, of that single photon source is exactly due to what you say. Yeah.
And so how robust is then this optimal control pulse against fluctuations in atom number?
Yeah, the fluctuations in the atom number is not a big thing, yes, because it only goes like the square root of n into the Rabi frequency. Yeah. If you have a fluctuation of square root of 1,000, let's say, of 1,000 atoms, that's 30 plus minus 30. That's a very small deviation in the parameters. Actually. There's actually more. There are other things that are more serious. Yes. For example, the atoms hitting the wall, simply. Yes. And then radiating 4 pi. Yes. After the dephasing. Or I should say, non-perfect blockade is also a problem. Yes, I mean, I realize the situation here, namely that there is no excitation of that the double excitation is completely forbidden. But that's not fully true. Yes. Actually, what happens is if you have two excitations, the dephasing rate of this two Rydberg state is so much faster that the emission of this doubly excited superatom goes in 4 pi and not in the forward direction. That is sort of suppressing this double excitation effect in addition. Yeah? So, I mean, the strong interaction in this case leads to a stronger dephasing than the motional dephasing of the single excitation. And that is, so the residual G2 here, this 0.2 is actually has also a sizable contribution of that. Oh, this can happen, yeah. I mean, you have some fluctuations here, yes. There's an error bar here as well, yes. It just means that there is some bunching of photons, statistical bunching.
With your
Maybe you could. Oh yeah, this would not work. The electron will bump into the wall immediately. Yes. So that's important. Yes, it's a very good point actually. Yes, this restricts us in the principal quantum number. We cannot go arbitrarily high. That's why we actually. There are many reasons, but one reason why we stick to this 40s is that the Rydberg atom is smaller than the distance to the wall.
But the traps, this effect very interesting.
In traps, you know, if you have a dipole trap, then of course the electron can go outside the dipole trap, and yeah, maybe the light shift is a little bit changed and so on, but the electron will survive this. Here it will not survive it; it will just bang into the wall. But there are actually other effects that are interesting that also have to do with this energy transfer. If you have a glass wall, yeah, you look at it, you think it's transparent, so nothing can happen, but that's not true because the Rydberg atoms, the Rydberg states do have transitions, very strong transitions to neighboring states in the gigahertz or terahertz regime. Yes? And glass, if you look at it, also has absorption lines or bands actually in the terahertz range. So you have to choose that Rydberg state such that there is no energy transfer of the electronic excitation in your atom to the glass material. So you have to know exactly what your glass material is doing. We did these experiments. I mean, Jim was working on this a lot when he was with us more than 10 years ago. If you take the wrong Rydberg state, then all of the energy is quickly dumped into the glass. And there are only a few principal quantum numbers that work magically. And 40s is one of them. And 32s is another.
So the first when the length of your cavity or like the vapor cell is longer than the Blockade radius, first it rises, but it seems to rise very fast. I would have expected it to rise like here it jumps like basically directly to 1. Why is that? I would have expected it to go like 1 over the number of superatoms or something like slowly up. Minus 1 over the number of superatoms.
Yeah, I don't know. This is something that I cannot answer. What is the curve? This is just a guide to the eye. It's not the field curve. Let's discuss this. Yes, I'm not sure. I mean, it's a complicated geometry problem. It's not round. The thing is not round, and has Gaussian profile and so on in the transverse direction. Yeah, I'm not sure how to answer this.
Do atoms which adhere to the glass contribute to the collective property?
Sorry? Oh no. They are totally out of resonance because of the surface interaction. And so if you take a medium atom in free space, then there is a surface potential, and they roll down basically, and the electronic structure totally changes, and they are not resonant with the light anymore.
You have a sense that it's a very thin vapor cell, small proportion of the atoms get to adhere to the walls.
So the typical range of these surface forces that we have to worry about is about 50 nanometers to 100 nanometers or so. I mean, we are accepting anything within the bandwidth of a gigahertz here. Yes. So that means, yes, if I say that cell has 600 nanometers, effectively it's maybe only 500 nanometer slab that is coming.
When you switch to something the infrared to the Rydberg condition, that might be more photoionization of
So far, we don't see that. I mean, everything is on a nanosecond time scale. That's a good point. We also in the other experiment, by the way, +1 and 4. Yes, but we have investigated this, and it takes place on a time scale of tens of nanoseconds. So let's say 50 nanoseconds or so. Everything here happens on the nanosecond time scale. Yeah? So it's fast enough. If you would do it for longer, then I fully agree. Then you would just blow everything up into here +1.
Talk about this percent enhancement.
Yes.
You have factor of 8. What are you actually aiming for?
Yes. So let's talk about this a little bit. That's it. Here, yeah. Okay. So here you see a simulation of that mode profile in that dielectric structure, and what you see is the field amplitude in color code. Yeah. And you see that it's mostly concentrated in here. Now, if you do the calculation of the percent effect locally, then you see that inside the structure, actually, the percent enhancement is even larger. Yes, it's 30 or 40. Yes, but then, of course, we have to integrate over the whole mode, because our experiment is sort of averaging over all the modes, and then what is left is an average percent effect of 8. That's what we directly see in that slope of that curve. Now, how to enhance that? There are various ways. One way is to modulate the size of those bars a little bit. That's called an alligator resonator, because it looks like peas then. Yes. That's well known in the literature. People like Jeff Kimball and so on have used that to enhance the percent effect even further. Yes. So the idea is that you basically go over to something more like a cavity. Yes. Where the light is sort of resonating at a certain wavelength with the structure in the longitudinal direction. So, this one here in the longitudinal direction is just, there's no resonance, it's just a propagating. Yes. But if you modulate, for example, the if you would modulate this here now, yes, then there's a little bit of Bragg reflection basically coming back and forth. If you do the analysis of this, then you get resonance. It looks a little bit like a Pfau, yes, and then you get further effects. How much? Ultimately, I mean, if you do this photonic crystal cavity like this thing here. Okay, the Q value that people have reached is 60,000. There's there's much to be gained. Yes. But this is not for our purpose. It's actually too strong already. Yes. We don't want to be that extreme.
This is what lunch after lunch. Take a very short break. Set up. So, join me in thanking Professor Pfau.